All right, so this is 3.1, Extrema on an interval. So this section is helping us to figure out what the graph of a function looks like when we don't even need to graph it. So we have a couple of theorems leading up to this. So the idea with this lesson is that we have some sort of function, and it may be some, quadratic or something that we just do not know. And so we will be given the function, and then we'll try to figure out what this graph would look like. And so this graph, we don't really know, but we know that there is some sort of squiggle happening. Okay, and so if we look at this as just the polynomial, we will be able to figure out, okay, well, there's a hump here, and it might kind of go up, and then it might go down, something like that, and we don't really know. It's just like some squiggle. And so what this chapter is helping us do is to figure out what this graph of the function looks like without actually plugging in numbers like this in good old Algebra 1, where you just make this giant XY chart and try to figure out what it looks like by plugging in numbers. So in the first lesson, 3.1, we find extrema on an interval. And so extrema are talking about the maximums and the minimums on your graph. So if we are just given just the function, can we figure out where it's turning up and then going down and going back up? So where are these, the min and the max located? So instead of just trying to plug in millions of points to figure it out, is there a way that we can say, okay, that's where the, this hump, this maximum is, and then this is where this minimum is on a certain interval? Okay, so that's the idea of this section. So trying to figure out, is there a way that we can use our derivatives to find where these locations are? So a couple of things of vocab, and then we'll kind of get into it. So extreme value theorem. So if f is continuous on some closed interval, then f has both a minimum and a maximum. So that's just saying if you're a continuous function, so remember that continuous just means that you can trace the function with your finger and you never have to lift it up for a whole, or because there's asymptotes, you can trace the whole way, and that is continuity. So if you have some continuous function, okay, so you can have like some squiggle, you could have a linear function, you could have a linear that's horizontal, okay? So any of those, you know that if you are continuous, then on some interval, so say you're looking, from here to here on some closed interval, then you are going to have a minimum value and a maximum value. So we know, okay, on this interval, if this was our squiggle, that's our maximum y, and this is our minimum y. On this interval, our maximum and our minimum are going to be equal because you're a horizontal line. Okay, and on this one, if this was our interval from here to here, that's our maximum and this is our minimum. Okay, so depending on what your function looks like, you'll have different values for your maximum and minimum, but this is just saying if you're continuous on that closed interval, you're going to have a minimum and you're going to have a maximum. Next one is about relative extrema. So relative extrema are looking at an open interval, okay, and seeing, as it is illustrated here, that in that open interval you have a maximum, or in that open interval you have a minimum. So here, okay, instead of looking at the entire function at once, we can say that there's these little areas where it's, it is a maximum, but it might be a relative maximum, not the most maximum point, but it is a maximum. So for instance here, this point here is a relative max because within, this open interval from here to here, it is the maximum value. Now if you look at the interval from here to here, no, it's not the maximum value, that is the maximum value, right? So depending on where you're looking in your graph, you can have a maximum, but it might not be the maximum. So those are called relative maximum. So that's a relative maximum, so is this one, that's also a relative maximum. Okay, again, because what if we took this interval from here to here? Then this value on f would be your actual maximum, right? So that's why it's a relative maximum. So it's not the most maximum ever, for this function. It's just in that open interval, that is the maximum value. Okay, similarly with your minimum values. So we have two relative minimums in this graph of f. So that's a relative and that's a relative with that same idea. So from this open interval from there to there, that's the minimum y value. In this open interval from here to here, that's the relative minimum y value. Okay, so if you included the entire, a larger interval, then you wouldn't have this is the minimum, okay, period. Okay, it's the relative minimum, because what if you included, and it extends and it goes down to here, then you can say, oh, well, now he's the minimum. Okay, so an absolute minimum is different than a relative minimum. Okay, so then the next type is critical numbers. Okay, so our plan for this lesson is try to figure out where these dots happen. Okay, and so instead of trying to plug in and figuring out, oh, okay, I guess it's kind of a squiggle, let's plug in some more points and figure out if we are right, there's some way that we can figure that out. So that's what we're trying to find. So when we look at this, if we know what a derivative is, okay, which we do, a derivative, right, is the, we can use that to find the slope of the tangent line at a point. So if we were looking at the slope of the tangent line, remember that we kind of visualize that with a ruler going along your function. So if we have this as our tangent line, we know that it kind of mirrors the function, right? So that's the tangent line there. It would come around. The tangent line's like that. Okay, we're going down. Then it's a negative slope, negative slope, negative slope. Then it turns. Here it's at 0. Okay. Then it goes up, and then it's a positive slope, and it goes all the way around, right? So it's always mirroring the where it is at the graph. So that's why we always said it was a tangent line at the point. Okay, so every point potentially has a different slope. So we have to be careful about saying that it is the slope of the tangent line at that point. Well, if we're trying to find these points, they all have something in common. Their slope of their tangent is always 0, right? So it's negative, negative, and then this is 0. Okay, that tangent line there is 0. Sorry, the slope of the tangent line is 0. Okay, same with up here. The slope of that tangent line is 0. Okay, and it's true for these others as well. So the slope of your tangent line is 0. Okay, and so that is very significant. If we're trying to find these quickly, instead of plugging in millions of numbers and hoping for the best, we can strategically find them by saying, well, we know it's going to happen when our tangent slope is 0. So let's just find where our tangent slope is 0. And so that's what a critical number is. So you know, okay, that these relative max and relative mins occur when the slope of the tangent is 0. So then we call that the slope of the tangent, okay, remember is your derivative at a point, okay, so that's f prime of c, equals 0. Okay, so that's the one of the ways to find these relative max and relative minimums. The other way is to see where the slope of your tangent line, which is your derivative at c, is undefined. Okay, so those are the two spots where you're going to find those. So remember that a derivative is undefined at a few different spots. One of them is a cusp. Okay, and so here you see that cusp. You also see it was an open dot there. Okay, so a cusp, when it is not defined because you have an open dot, okay, that means that your derivative is not defined. You can't take the derivative at a number if that number doesn't exist. And you can't take the derivative at a cusp because the derivative coming in from the right is different than the derivative coming in from the left. And so therefore your derivative does not exist. Okay, so there are two cases where you're going to have a critical number. So when your derivative at a number is 0 and when your derivative is undefined. So those are the two ways that you can find these locations very quickly. Okay, so one is that you take the derivative of f, set it equal to 0. Those are going to be your spots where you have a horizontal tangent line. And so that can be a possibility of where you are going from a max to a min. It doesn't necessarily mean it has to be one, but that will be true when that happens. And then the other is where you have your derivative being undefined, and so that can be a cusp, an open dot, things like that. Okay, so those are your just knowing about derivatives helps you because now you don't have to, plug in zillions of numbers to try to figure out what your squiggle looks like. You can actually be strategic and find, okay, well, I know it's where any possibility is where your derivative is 0 or your derivative is undefined. Okay? So that leads us to our theorem. So a theorem of relative extrema is that they only occur at critical numbers. Okay? It does not say that they have to occur at critical numbers. Okay? So when you find this critical number, you don't just blindly say, there it is, and he's a max or he's a min. Okay? But it does mean that that's your possibilities. So when you find all of these places where your f prime of c is 0, those are all the options you have for where your relative extrema will be. Okay? So let's try this with a couple examples. So we're going to be given some odd-looking polynomial that we don't necessarily, know what it looks like or are familiar with, and we're going to be trying to find the extrema of it. Okay, so here's that same polynomial that I wrote up before. We're going to try to find the extrema of that polynomial. So where are the relative max, where's the relative min, where are these things? So we need to go through and figure out where our critical numbers are, okay? Because we know that that's where they would occur. Okay? So they would occur at critical numbers. Well, a critical number is where your derivative is equal to 0 or your derivative is undefined. So let's go through and find them. So we are given f, so we need to find our derivative so that we can start talking about that. So that's 12x cubed minus 12x squared. Okay, we want to find where that derivative is equal to 0 and where that derivative may be undefined. Okay, so equal to 0, we can pull out a 12x squared, right? And then an x minus 1 is left over. So you know from your Algebra 1 days that your zeros, which we're going to call critical numbers, okay, so our critical numbers are at x equal to 0, right? Or x equal to 1, and actually and x equal to 1. Okay, so those are our critical numbers. Again, we don't know that these for sure are like, oh, he's the minimum, that's the maximum. Okay, we just know that if there was one on this interval, that's where it would occur. Okay, so that's where your relative extrema would be. Okay, so now let's see, we are trying to find the extrema, not the relative extrema. We're trying to find the extreme. So who is the largest y value and the smallest y value, okay, on that interval. So this interval is very important. So far we know something happens at x equals 0, something happens at x equals 1, and then we're looking on a certain interval. So we plug these into our f, okay, because we're trying to graph f, right? So we're going to plug in our 0 and our 1, so let's plug that in first. Okay, we know that we're also going to have to figure out, where this guy came from. So we're going to try -1 because he's in the interval. 2 is the last one on our interval. And then any critical numbers in between. So we know we have a critical at 0 and we have a critical at 1. So we plug that in. This guy's 7, 0, 1, 16. Okay, so we know from this, okay, so we know that there was critical numbers here, and then we pulled these two because that was the interval we were given. So at -1, you're 7. Okay, at 0, you're 0. 1, you're at -1. And at 2, you're at 16. Okay, so that is our squiggle. Okay, we know that somehow it's connected. We don't really know concavity or anything at this point, but somehow this is all together, connected. Okay, so that's kind of our rudimentary graph. We don't know what it looks like, but it is connected in some way. So we are asked find the extrema. So you want one y value that is the maximum and one y value that is the minimum. Okay, so you're looking at your y values. So if we're looking at our graph, we can see that our minimum y value is right there. Okay, and that point is 1 comma neg 1. Okay, and our maximum is right here. And this one is 2, 16. Okay, so we were asked to find the extrema. The extrema are the y values. Okay, if you want to write this as a sentence case, so they asked you find the extrema. The extrema are a minimum, okay, is found, and you can say this a few different ways. You can say the minimum is found at x equals 1. Okay, the minimum is negative 1. Okay, the definition of the minimum is the y value. So you say the minimum is negative 1, and it is at x equal 1. Okay, so that's one way that I could write that. Okay, so just make sure that your minimum is a y value. So then our maximum is our y value, which is 16. And that's at x equal 2. Okay. All right, so go ahead and pause this now so that you can do this next example on your own. All right, so you should have already done this example. Okay, try this one on your own before you listen to the explanation. All right, so if you are finished, okay, your first step was to find the derivative. So your derivative is 2 minus 2x to the negative 1/3. Okay, if you did your derivative correctly. Okay, remember that our criticals are where the derivative is set equal to 0 and where the derivative is undefined. So we have to look at both of those. Okay, and this one here, it was a nice polynomial. Nothing was in the denominator or anything like that except for 1. So this one, nothing made it undefined. Okay, but this one we know that something's up because we have a cube root. It's negative. You know, we need to look at this carefully. So first we can look at it with the zeros. Okay, if you pull out a 2, you'd be 1 minus this x to the neg third is 1 over x to the third, right? Or the cube root of x if you like to write it that way instead. So now we can figure out, okay, where are our critical numbers? Well, our critical numbers are when this one is equal to 0. Okay, 1 minus 1 over x to the third is equal to 0 when, you need to see this, you would subtract the 1, right? And then you would multiply by neg 1, so then you get 1 over x to the third is equal to 1. And so 1 over x to the third is equal to 1 when x is 1. Okay, so that's one of our critical numbers. The other critical number is where this is undefined. So you know that this is undefined when x equals 0. So then that's our second critical number. Okay, so then now we just need to plug these in along with our interval to see what our graph would look like. Okay, so we grab all the numbers that we are given. So the interval is neg 1 to 3, and then we found two critical numbers. It was 0 and 1. Okay, so we're plugging it into f to see what our f looks like. So we got negative 5, 0, negative 1, and it's negative 0.24. Okay, so again, at negative 1, we are negative 5. Okay, at 0, we're 0. 1, we're negative 1. Let's move it up there. And then at 3, we are at negative 0.24. So we're really close there. Okay, so again, we don't really know how this is connected yet. Okay, but we know in some way they're connected, so we can just kind of sketch that just to kind of give us a visual. So now we need to find our extrema. So remember, our extrema are the y values. So you're looking at your y values. Who is the minimum? Okay, so that's the minimum. And then who is your maximum? So the largest number of your y is actually 0. Okay, so then you write your sentences. So minimum is -5, and it's at x equals -1. The max is 0, and it's at x equals 0. All right. So this is your 3.1. Okay, so make sure you finish all of your homework in class today.